my name is Damon Tordini. I'm the Product Manager for Flow Simulation here at Hawk Ridge Systems. I'm based out of our Irvine webinar for 2015 today on December 16th, and we're going to be wrapping up a series of webinars we've been talking about this year with regards to how SOLIDWORKS Flow Simulation is used in some different industries and how it's applied to solve some common problems. And specifically today, what we're going to be talking about in more detail is something that I've mentioned a couple times in the previous webinars that we've done, which is a capability inside Flow Simulation called the Parametric Study, which basically enables you to try out a lot of design variations and test a range of different operating conditions as well as design modifications to finally hone in on what the best possible design is going to be in a variety of situations, not just one. Before we get started here, let's just review a little bit about the GoToWebinar interface that you see on the side of your screen. As far as the audio, you should be able to either use the microphone on your computer, whether it's your laptop or desktop, as long as the audio mode is set to use mic and speakers. However, if you want to try something else, if you have any issues or your speaker isn't loud enough, you can also switch to the use telephone option. You'll need to click on the radio button, and basically the phone number will pop up for you that you'll need to dial into, as well as the meeting ID number. So hopefully you've been able to get one of those two options. We'll kind of verify with everyone in a minute here that everything's okay. Also, for visibility, you can scale the viewing window once you've decided how large you need to see the text. You can zoom in, of course, and you can make it full screen. And of course, if you have any additional questions, just ping a question into the chat panel on the side. You'll see that there is a questions interface which you can use to ask about the audio or video of the GoToMeeting, or of course any of the content during the presentation. And so just to confirm that everyone's able to see my screen and hear me okay before we start with the content, let me just pop up a quick poll here. And if you get a chance, please reply to that just so we can confirm that everything's working. Okay, it looks like everyone can see properly. And let's just confirm that the audio is okay. Okay, and if the audio is cutting out a little bit here, sorry about that. Looks like we might be having some bandwidth issues. I'll try to go a little slow just to be sure that we don't miss anything. All right, well, thanks again for confirming that. I'll try to increase my volume here a little bit. So let's dive into the contents of the webinar today. What I want to start with is a simple question, looking at a common product many of you may have seen. This, for example, on the right-hand side is a globe valve, one of the many types of valves that some of you may have seen or are familiar with. And we all know that one of the main benefits of SOLIDWORKS Flow Simulation, as well as the other simulation tools that we have inside SOLIDWORKS, is the ability to set up a simulation to test for some kind of operating conditions and requirements and make a quick change, figure out how is that product going to be refined to meet its tasks most effectively. But a lot of products don't really just have one operating condition. Aside from the fact that you probably have a lot of different, let's say, loading conditions, or in the case of flow simulation, maybe different flow rates or even different fluids that you need to test the same product for, there are also a lot of products that have moving parts. And those products, if they have moving parts and maybe are configured differently for different kinds of situations or operating conditions, make it a lot more difficult to try to figure out what the best design is in all situations. For example, if I were to change maybe the inlet diameter of that valve, what does that do to the flow rate and pressure, not just when the valve's fully open, but other situations? So the solution is to be able to change the design of the model much more rapidly than you could whether you're exporting a model to another program or even if you were just talking about a traditional design change in SOLIDWORKS. And so luckily in SOLIDWORKS Flow Simulation, we have the ability to do that, where we can basically run a large batch of studies in a lot of different configurations and compare them quickly to answer those kind of big picture questions. So again, the product that we're focusing on today is SOLIDWORKS Flow Simulation, which is our built-in CFD tool in the SOLIDWORKS family. There are, of course, other simulation products that can solve anything from stress analysis to vibration or injection molding, and those programs also have their own versions of this kind of an optimization or quick batch run. But in SOLIDWORKS Flow Simulation, we call it the Parametric Study. Now, just in case you're not familiar, to give you a brief background here, Flow Simulation is what we call a general purpose fluid flow and heat transfer tool. So basically, it's used to solve a wide range of problems, anything from pipe flows, industrial equipment, heat transfer for electronics, aerodynamics, all sorts of situations. But it is what we call a powerful 3D design simulation tool, basically meaning that it gives you some pretty advanced physics, but in a very easy interface and a very user-friendly situation, which is integrated into the SOLIDWORKS environment, with the whole purpose being to break down the traditional barrier between the designer of a product and an analyst who would need to have expertise in CFD to be able to analyze something and predict its performance. And of course, if you're trying to rapidly iterate a design up front like this and try out many changes, you can't rely on an analyst to go and run a simulation for you every time you change something. So we need a program that lets you do it all at once. So let's look at a case study here of where we might need to change a design very rapidly and try out a lot of different configurations. So this is a globe valve. It's a simple type of valve that's basically got what we call, well, you can basically see it's a sort of circular handle, and basically would be threaded so that if you turn that, of course, the globe valve itself would lower down onto the seat and slowly shut off the flow. And in general, you probably, when you're designing a valve like this, want to design something that has a shut-off curve, a valve lift curve. So something that doesn't suddenly release a huge amount of flow with a small amount of turn. So when we're trying to evaluate what the best design of a product like this is, of course, we could look at some design changes, maybe, for example, changing the angle of the plunger. But if we were to change little minute details, like for example, the angle of the sides of the plug, we know that in some situations, for example, when the valve's fully open, we probably won't see a significant change in any of the results. And of course, if the valve is fully shut, we wouldn't see a change in the results. So somewhere in between is where that design change is going to have the most impact, but we may not know exactly where that is. So to sort of get the broad scope of what the right design is going to be, we need a way to simulate all of these positions for the different design changes pretty quickly. So let's dive into the software and start to look at how we would evaluate and compare these two designs and figure out once and for all which one's better. So I'm going to launch SOLIDWORKS Flow Simulation 2016 here. This is the most recent version of SOLIDWORKS, released about 6 weeks ago at this point. And I'm going to open up this part file that I've modeled here. This is a multi-body part file, or of course the other option would have been to make this an assembly. But basically, if I start with my finished product, the first thing I really just need to do is turn on the Flow Simulation add-in. That's going to let me double check that the model is ready for simulation and set up the rest of the conditions. So let's do a quick section view here and take a look at what we're comparing. Using the little favorites menu in the feature tree, you can take a look and see that I have a sketch which sort of describes the shape of the seat of the valve and the plunger. So right now I've got a particular angle in there. This is kind of the default design. And I want to compare it to maybe something that's a little steeper. And this is the fully open valve situation. So let's set up an analysis to see what our, for example, flow rate would be with a known pressure for this condition. If I want to do that, I'm going to need what we call an internal study in SOLIDWORKS Flow Simulation, which is going to evaluate some sort of fluid inside the model that I've created. Of course, we could also do what we call external. The only requirement for that would be to cap off the ends, and you can see here that I've got what we call some lids, which have been automatically created to close up those openings, and that'll allow Flow Simulation to detect where the fluid boundary is, and also it gives us a location to put in our flow conditions, our flow rates, our pressures, whatever they may be. So we can verify that Flow Simulation has detected that fluid region. It shows up in blue right there, and then we can start the setup. So let's jump into what we call the wizard here to create a new project. And we can just say that this is, for example, revision A, maybe baseline design, fully open. Since we can see that in this configuration, the valve is at the fully open position, which should have the maximum flow rate. So we'll step through the wizard here. We'll do some basic things like pick our unit systems. Maybe, for example, we want length to be in inches or some other parameters. We can customize those and save them. And then we can set up the scope of the analysis. And we've already talked about this being an internal study. And then you can see some of the physics that we would be able to turn on if we were doing a more complicated analysis. For example, we could account for heat conduction to find out how hot or cold any of the parts might get. We could include gravitational effects. We could even include rotating components like impellers or compressor blades. For right now, none of these are going to be necessary. So we'll just continue here and select what our fluid is going to be. And we're just going to choose water for this one, simple water valve. Although you can see that we have a variety of liquids to choose from, as well as other types of fluids like gases, or even less common things like non-Newtonian or sort of organic liquids. You'll also notice that if I wanted to, I could account for the cavitation in the water that might be occurring if the valve is near the fully closed position, which of course, if there's bubbling, could affect things like the efficiency or cause pitting or other problems. We can set up some wall conditions like roughness if we want to. And then of course we can plug in our initial conditions. And for right now I'm just going to use STP, standard temperature and pressure. So basically a normal room environment. And the wizard at that point is done. The last thing that we have to worry about here are the flow conditions themselves. And so we can create what we call a boundary condition. And for boundary conditions, we really have two choices. If we know that a particular opening is an inlet or an outlet, and we know something about the flow rate at that location, we can define it as such. So for example, if I knew that I was trying to get 100 CFM through this valve, I could define that as an inlet flow rate, and then I would be able to see things like the pressures. But for a valve, more likely what you probably have is a pump somewhere upstream that's providing a certain amount of pressure, and what you want to know is what the flow rate's going to be. So instead, we could define what we call a pressure opening, and we could, for example, define this by static pressure. And you can see that we've got the absolute value of our pressure in here. It says 14.69 psi, which is 1 atmosphere. If we want, let's say, 1 psi of pressure head, we can simply increase that by 1. And you can even do mathematical operations if you want to. You could say -1 or +1. So we'll assume 1 psi above atmospheric is coming in. And then at the other end, again, since we don't really know what the flow rate's going to be yet, I can do another boundary condition. This time we'll create what we call an environment pressure, which technically could be an inlet or outlet, depending on the other conditions in the simulation. But in this case, we're pretty sure that it will end up being the outlet, since we're defining this as just atmospheric pressure, basically open to the environment, and there won't be any resistance or back pressure. So really, those are the only physical conditions I need to set up my analysis. Before running this, the other thing I'll do is create some goals, and those are the key measurements or key information that I want to know. For example, what is the flow rate? And I can create something called a surface goal at the outlet to figure that out. And I could also, for example, measure things like the average velocity. So at this point, we could mesh and run the simulation. The meshing controls, of course, are highly automatic, but you can also modify them and choose the level of refinement you would like, as well as manually refine the mesh in specific areas if you wanted to. So we could bring up the solver. This is going to automatically mesh and run the calculation on my local computer using all my multiple CPU cores that might exist, although just be aware that you could run this on a networked machine as well if it was faster. So we have the solver window pops up. It's quickly generating the mesh. It's going to start to solve, and we'll even be able to preview what the results are before the calculation is finished. That's one of the benefits of setting up the goals. We can see here we'll have some trend lines if I unpause this, and we'll also be able to bring up a preview plot where we can actually see things like pressure or velocity as the simulation develops and the solver hunts for the final answers. So again, we get some pretty interesting results here. But if we look at the final results of this analysis, the fully open revision A, and then also we could, of course, clone this and look at what we call revision B, which is really just a slightly modified version of the plug. Again, you probably wouldn't see a major difference in this situation because the valve's fully open. There's not going to be that much more restriction depending on which design we choose. We could, of course, use things like the compare tool to evaluate that, and that will allow us to very quickly bring up the goals that we had created, as well as some of the other result plots that we might want to look at, like cut plots, for example. And so looking briefly here, we can see this is a cut plot of the velocity between the two designs, and also we could go to our goals, look at the average velocity, the flow rate there, and also a turbulence parameter. And again, we can see that there's very little difference between those two designs. So how do we evaluate which is the better design across the full range of conditions? Well, that's where the parametric study comes in. So we know that this valve would have a lot of different operating situations, and maybe in some cases what you would need to evaluate is maybe just a different flow rate or a range of flow rates or a range of temperatures or other simulation parameters. But for this product, we not only need to account for potentially different parameters or inputs, but different geometry. The valve itself has to move. And so that's where the parametric study is going to come in. So we can activate a project and we can create a new parametric study. And essentially, the parametric study allows you to set up as many design scenarios as you want, where you can vary those conditions in the simulation, or you could also vary dimensions of the model. So for example, if I knew that I wanted to move the valve up and down and to simulate the different positions of lift, I could click Add Dimension Parameter, and it's as simple as bringing up the sketch and selecting the appropriate dimension, which in this case is on the right-hand side here. So right now we're at 3.5 inches of lift. Then all I need to do is specify what the different values are that I want to try, and you can either type them in manually, or also we have some options like range with number or range with step, and that lets me do things like plug in the minimum and maximum positions, and then maybe how many design iterations I want to try based on the spacing. I could say test it every 1/2 inch. So that's going to create all of these scenarios, and then I can also choose which goals are important, the velocity, flow rate, and bulk average turbulent intensity in this case. Let's just look at these two. So at this point, I would hit run, and this is going to run through and calculate the study basically 7 different times with that valve moving every time. I could start it here, and of course you'll see that it brings up the solver again, and it's basically going to recalculate what I had just shown you a few minutes ago, And on the screen in the graphics area, you can see the preview of what that situation would look like, what that version of the model would look like. Here's half an inch of valve lift, which is almost all the way closed. And basically, again, we would just wait for the simulation to calculate this 7 times, go get a cup of coffee, grab some lunch, come back. In this particular situation, luckily the studies don't take too long, and it would probably be about maybe 10 to 15 minutes overall to get the full batch of results. So I can just stop this prematurely here, and let's go check out the one that we had run before and compare this. So here's my valve lift parametric study. You can see again I have these 7 scenarios of different lift positions. And once everything's calculated, I immediately get a nice table showing me what the volume flow rate is for all of those different positions, what the velocities are and the turbulence and any of the other goals that I might have created. And you can export all this data to Excel if you'd like to plot it yourself, but it's actually just as easy as clicking over to the Goals tab, and you can immediately get some charts or also bar graphs that show you these trends instantly. So for example, if you look over to the right, the volume flow rate plot is showing you what that flow rate is versus these different scenarios, where the first one is half an inch and the last one is 3.5 inches or fully open. So we can see what that curve looks like. This is the valve lift curve, which you can see has a little bit of sort of a shallow start. In other words, the amount of flow rate increase is a little less than linear at the beginning, and then it kind of levels off again at the end. So if we were trying to get something that was a little more like a straight line, now we could change that design. We could copy our whole project, which would also copy the parametric study. And then we could sit on the whole parametric study again and see how this change in the angle of the sides of the plug affects all of those positions. So again, here's our other valve lift parametric study. We would run this, it would take another 10 to 15 minutes, and then once again we would have our curves. So now we're able to evaluate not just 2 designs or 3 designs, but we can evaluate these designs across a whole range of different situations, configurations, geometry positions, operating situations. So as we find out, it looks like making that shallower angle does seem to make it the valve operate a little more predictably at the near closed points, but it also tends to make the flow rate kind of drop off as it opens up the rest of the way. So maybe we need some more tweaking to make sure that when you open the valve, it doesn't all come out kind of at the beginning. Another situation where the parametric study is really valuable is when you know you have a specific goal that you need to meet, maybe a specific design requirement, and there's maybe one dimension that you know has the biggest impact on that requirement. So here's a situation, a car exhaust, where we know, for example, that picking the right size tubing is a key design choice. And if we knew what kind of parameter we were trying to meet, we could use flow simulation to basically figure out what that ideal diameter of tubing would be to meet whatever operating condition we're trying to get. So for example, with the case of automotive exhaust, you typically want to maximize the exhaust velocity. That helps what we call exhaust scavenging effects. And you definitely want to limit the back pressure as well. You don't want too much resistance. So a lot of times designers are trying to pick an exhaust that provides just the right amount of back pressure. So if we knew what that value was, we could use the parametric study in flow simulation to automatically find the value of a dimension that gives us that output. So this is similar to the optimization mode of the design study in SOLIDWORKS simulation. So let's take a look at that project here. This is really just from the catalytic converter back to the end. Again, I've got my lids created here, and my fluid region, of course, has been automatically detected inside flow simulation. So the first step would be to set up the project with the wizard, the same as before. In this situation, we've got an inlet mass flow rate based on the engine displacement. And we've got a pressure condition at the outlets, just representing that that is the surrounding air, right, in your garage, hopefully with the door open. So we also got some goals here, and you can see that I've got a goal measuring the static pressure at the inlet, as well as a goal measuring the pressure at the outlet. And if I want to know what the pressure drop between those is, which is also called the back pressure, I can simply create what we call an equation goal, which is the difference of those two. The simple formula that I would type in just like in Excel. So once I run this analysis, I will be able to see what the results are for my initial design. And in this situation, I've started with 60 millimeters here. You can see again, I've got the sketch profile saved to my feature tree, and I can go take a look at what that is. So 60 millimeters for the diameter of the tubing, and I've also got some creative modeling techniques in here where when I modify that, it's also going to adjust the diameter of the exhaust tips, just to make sure I got sort of the same cross-sectional area. So again, looking at the results from the default design, I can see that right now, according to the goals that I created, I've got about 1.2 psi of pressure. And that's the pressure drop, so back pressure. And in my situation, I was trying to get something more like 2. So this exhaust is actually oversized at the moment. So I know I need to reduce it, but the question is how much. And so the parametric study can get me that answer automatically. This time, I can create another parametric study, but the difference is instead of what we call the what-if analysis, I could switch the mode to goal optimization. The change there is that you can only modify one parameter, but instead of having to input what different sizes you would like to try for that dimension, instead you can simply put in a range and then tell the parametric study what kind of output you're looking for, and it will find the value that provides that output. So I've selected goal optimization mode. I've picked the dimension that I want to modify, which is the currently 60 millimeter diameter of the exhaust, and I've put in what the range is here, 50 to 70 millimeters, somewhere in there. My criteria is the thing that I'm trying to achieve, and in this case, it's that pressure drop of 2 psi. So again, I would pick whatever goal I had created to measure that. Here I've got my pressure drop, and I would put in what the target value is. And you can also put in a range or some sort of a tolerance, basically. Here I'm allowing plus or minus 1/4 of a psi. Then, of course, I can pick whatever goals or other output parameters I want to see once the table is fully filled out. I would go to the Scenario tab, and I would run this from the beginning. And again, what it's going to do is modify the design. In this case, it's going to try the maximum first. It's going to go back and try the minimum and repeat that back and forth until it finds a value of that dimension that results in a value of this goal that's within my range that I had specified. So we can see, for example, that 70 is too big. It's going to go ahead and try 50 millimeters now, which is smaller than what we had. And once it solves that, we'll see 50 is actually too small. That results in too much pressure drop. And again, the simulations here, of course, are using all of the CPU cores on your machine. And the nice thing about the parametric study is that you can actually have flow simulation run up to 2 studies simultaneously, which can speed up the generation of the parametric study even further. So here I'm running scenario or design point number 3, where the parametric study is trying about 56 millimeters. And we're very close there. You can see that the pressure drop on the 3rd try was 1.73 psi. So it's just kind of below our range. And so it's going to do one more attempt at about 54.5 millimeters. Maybe 55 if you round up. And as it turns out here, once the solver finishes, once again with whatever kind of automatic mesh it had generated, we get a message saying solution converged. And so that means it's finally found a design point which did have the value of the goal within the range that I had requested. And so once the optimization's finished, I can go right to that design point and I can create a new project out of it. And that will allow me to see all the full results like I normally would want to see. For example, any other goals that I had created, but more importantly, any of the visual plots that I might be interested in. for example, flow trajectories or cut plots. So I can immediately tell not only what the best design is for this particular goal or operating condition, but then I could also evaluate how well it performs for other situations. So the overall point is that the parametric study is a powerful tool that, being built into the flow simulation software, allows the user to run a large batch of studies almost simultaneously without any extra input from the user, and generates much more data than you can get out of just one analysis, and allows you to answer sort of these big picture questions about what product is going to be the best operating in all situations. And of course, there's just some other examples of products that are commonly analyzed in flow simulation: ball valves, heat exchangers, medical devices. And basically, if you can model it, you've created it in SOLIDWORKS, you can optimize it just by selecting the same dimensions that your model is built off of. Just to give you a little bit of background on flow simulation, of course, we have thousands of companies that are using flow currently. If you take a look at some of the online resources from both Hawkridge Systems and the SOLIDWORKS website, you can get some more info on who's using flow simulation, for what kind of applications. And again, of course, you can contact myself or Chris or your account manager, and we'll get you any information you might be interested in. Another thing that we want to make you aware of is that in addition to selling and supporting the software, Hawkridge Systems also provides analysis services. So if, for example, you have a time crunch and you need a simulation job done very quickly, we can actually do that for you. We can either provide you with result reports, or we can also provide you with mentoring and train you how to do it on your own the next time. And the nice thing there is that any services dollars you spend with us, we will give you a partial credit back towards the purchase of any simulation software. Okay. Just to wrap up here, we basically are nearing the end of our Webinar Wednesday schedule for the year. The last presentation is going to be at 11 a.m. here, which is going to be SOLIDWORKS Assemblies 101, and then we're off next week for the holiday break, and we're coming back to you in 2016 with probably some new formats for the webinars, and hopefully some new interesting content that many of you will appreciate. With that, I just want to say thanks again for attending. If you have any other questions, please feel free to plug those into the questions chat panel on the side of your screen. Chris and I will try to get to them. Otherwise, if there's nothing, have a great rest of the week and happy holidays.